What do I do? Do I
No, it was fine. Leave that muted because it's going through this.
Someone is saying I can't hear the speaker now.
Can you hear us now? I think it's working. Go ahead.
Okay. Am I audible?
Yes.
Yes.
Share your screen, share this the presentation and go ahead. You can see it if you want.
It's already been shared.
All right, there. Now full presentation mode and go ahead.
Yeah. It was fine.
Go.
So, hello everyone. Good morning, everyone. I'm Manashita Borah. I'm a Fulbright Fellow in the University of California, and I'm in the lab of energy controls and applications. And I'm an assistant professor in the Department of Electrical Engineering, Tezpur University. So I'm here to share with you a bit of our research, the current research that we are doing in our lab. So here we start with the contents. So the first is a recent survey on battery production. So this survey is not literature survey exactly, but the current industrial survey that I have done. So next is shifting from NMC to LFP. So NMC and LFP are both lithium-ion batteries. And there's a current drastic change of shift towards LFP. Though LFP has been there, but now there's a drastic change. So we shall see how and why. Fractional order models, physics-informed machine learning, and a few fractional order modeling and control applications that I have applied in other relevant areas. So this is like not a mandatory part of the slideshow, but we can go through them if we have time. Okay. So now we come to the battle of the batteries. So this is LFP versus NMC. So I have carried out a SWOT analysis. Now LFP is lithium ferrous phosphate. It is cheaper, it is more safe, it has a longer lifetime, and of course there is abundance of iron on Earth. Whereas NMC, that is nickel, manganese, cobalt, its strength is that it has high energy density, low temperature performance, means you can also charge the battery even when there is a freezing temperature, like in Colorado, whereas that the same is not applicable to LFPs. It has problem while charging and performance in low temperatures, and NMC has high power density. Now, the weakness of LFP is heavier, so it's considerably more heavy than NMC batteries. It has relatively less amount of energy density. Again, low temperature performance. There is a poor performance when the temperature is low power density. And NMC weakness is just the opposite of its strengths, like it's more expensive and safety. So those batteries which usually blow up due to thermal runaway or cause explosions or fires are mostly NMC batteries because they suffer from a phenomenon called thermal runaway, and where there is continuous heating of the heating phenomenon in the battery chemistry, and it might blow up. So there is an issue of safety, and whenever we work on batteries, safety should always be the first priority. Next is nickel cobalt supply chain. Now since the Russia-Ukraine war, a major part of nickel and cobalt came from Russia, and now since the war, there has been a lot of restrictions on the supply chain. So what people are doing, people are looking for alternatives. So what if there is no NMC batteries anymore? We will be left, we must have an alternative to it. So, and next is a lifetime. A lifetime is relatively shorter. So for example, in an electric vehicle, the lifetime is around 20 years we consider. And the NMC has a lifespan of 10 years, which means approximately after every 10 years, we have to change the battery. So that is kind of half of it survives only half of the lifespan of an electric vehicle. So NMC, a shift from NMC to LFP is required. Next is opportunities. So these are the opportunities, low, mid-range, entry-level electric vehicles, e-bus, e-bicycle, stationary storage, where weight is not an obstacle, cost-sensitive application because it is cheaper. NMC, again, long-range, high electric vehicles because it has high energy density and power density, and of course, power tools performance. These are the LFP threads. So NMC and high voltage LNMO, and sodium-ion battery, regulations of energy density, increasing material cost, and NMC threat would be, the regulations on thermal propagation because it kind of explodes during thermal runaway, and increasing raw material costs. As I said, most of it comes from Russia. So industrial shift to batteries. So this industrial survey is basically carried out for the last 2 years. So in 2020, BYD Byte, which is a Chinese conglomerate company, introduces its LFP blade battery that has increased its pack level energy density. So in the previous analysis, we found that the energy density of LFP was low, but they have introduced new research where this battery has kind of more energy density. So with this LFP's additional advantages in cost and safety, it is cheaper and safer. There is an increased demand in LFP. In May 2020, China, the production of LFP surpassed NMC for the first time in 3 years. March 2021, Volkswagen announces LFP for all of its entry-level battery electric vehicles. And the last is October 2021, which is a big jump. Tesla announces switch to LFP batteries for all standard range vehicles globally. So now, the next generation kind of batteries will be the LFP batteries. So this is the EV original equipment manufacturer. So first is Volkswagen, and the kind of chemistry they produce is LFP, then there's Tesla, again LFP, and high nickel, manganese, cobalt. Then there's General Motors, Ford, Stellantis, Renault, and Volvo. So they are now presently manufacturing NMC, but they are gradually shifting to LFP. Now there's an open problem. There's a problem with LFP batteries. Even while we're trying to shift, there's a major problem. The first is SOC estimation of LFP, that is state of charge estimation of LFP. Now, why is it an open problem till now? The problem is you see the open circuit voltage and the state of charge graph. There's a flat portion in the middle, if you can see, where the charge reaches from 0 to 1, like from 0.2 to 0.8 is a flat portion. And that flat portion makes it difficult to estimate the state of charge. So, and state of charge estimation is immensely important to determine the battery health parameters, to know how far the electric vehicle will last or drive, it will depend how far the vehicle will drive, depending on the state of charge. So a correct and accurate estimation is very much required here. So what we are trying to do is, in the current research, we are trying to introduce two methods. The first, okay, these are the broad objectives. Let's go to the broad objectives first. So understanding the physical behavior of battery supercapacitor hybrid energy storage systems. So we are introducing fractional order modeling framework with offline chaos-based ML techniques. Next is investigation of real-time database feedback in improving accuracy of battery charge and prediction. This will be adapting to the dynamic conditions. And last is benchmarking the role of smart hybrid energy storage systems. So these are the broad objectives, but currently we are focusing on LFP because we see that there is a huge prospects of LFP as everybody is shifting towards LFP. So we are introducing two tools. The first is fractional calculus. This is fractional order modeling, and physics-informed machine learning. Now, why fractional order derivative? The first is that it is a non-local operator. So unlike integer order derivatives, we see that in integer order derivatives, it's a memoryless operator, whereas in fractional order derivatives, we calculate the derivative depending on the past values of until the present time, past values of the function until the present time. So it has kind of infinite memory, you can say. Next is it is a non-ideal operator. So it can incorporate non-integer values as well. So even if we want to work with integer order derivatives, it can still be called a fractional order derivative as well, because it is a subset of fractional order. So kind of all integers are fraction. So it is kind of superset of integer order systems. Last is flexibility and stability. The additional fractional order parameter gives more flexibility and a larger stability region. So how? Because let us take an example of a normal PID controller. In a normal PID controller, you have only 4 points to choose from, whether it's PD, PID, PI, and P. 0, 0, 0, 0, 1, 1, 0, 1, 1. But when it comes to fractional order controllers, you have the entire area left open to be chosen. So you can choose any point within that space because alpha varies from 0 to 1, not just 0 and 1. So how are these advantages relative or relevant in our case? So when there are so many cases, just like we miss out on so many points in an integer order system, there are so many inherent dynamics of an LFP battery which are not captured by integer order derivatives or integer order modeling. And that is where fractional order modeling comes into the picture. Fractional order modeling tries to capture the underlying dynamics which were otherwise not captured by the integer order models. And why physics-informed machine learning? Now, in regular physics, regular machine learning techniques, they require huge amount of data. First, you have to train it, then test it, then validate, a huge amount of data, a lot of experiments. Whereas in case of only physics-based models or an electrical equivalent model, you require small amount of data, but it highly depends on physics. So one is a black box model, one is a white box model. What if we combine the best parts of both the systems and make it what we call in our lab a zebra model, black and white? So it is kind of introducing physical laws into the neural networks. PINN means physics-informed neural networks, a basic ML algorithm, and as well as some amount of data. So if you see the second row, it doesn't require large amount of data. It requires just some amount of data, maybe half, and the rest of it is supplied by the physics-informed or the physics model. That is the electrical equivalent circuit. So this is the electrochemical impedance spectroscopy of LFP cells at our lab, ECAL lab, UC Berkeley. So these are the LFP cell that we are conducting, and we are introducing a current to it, and we are observing the output voltage. And these are the HPPC voltage results, high pulse voltage results. And we see what we have done is that we have varied the LFP SOC from 10% to 90%, as you can see. And then we tried to observe its drop in the voltage and the EIS spectrum on the right-hand side. Next is, so these are the circuit elements that are usually used. That's R, that stands for the bulk charge transfer at the interface of the battery, then C, then CP, L, and LA. So in our case, we are considering R, C, and CP. Now CPE, the constant phase element, has a fractional order alpha, as you can see. So decreasing alpha. So alpha varies from 0 to 1. So decreasing alpha, as you can see, the semicircular part of the EIS will go on becoming smaller. If we increase it, it will go on becoming larger. The radius becomes larger. So what we can do is we can fit it accordingly to our need. So next is the blue one is the EIS spectrum data, and the red one is our fitted data. fitted function. So we are using different kinds of circuits. The first is R0, R1C1, then R0, R1C1, and then R2C2, and like from left to right. And we find that in the lower row and right bottom, it starts fitting, our circuit starts fitting the data. As you can see, the red line overlaps the blue line. So we, even though we tried further increasing the number of circuit elements, but we don't want overfitting. So we chose the right bottom circuit to be our selected circuit. So
what is CPE
it's
again?
constant phase element. So that is where the fractional order part comes into picture, because it has a power alpha. So now it is the EI spectrum, and this is on the right, and we see that there's a circuit that we have selected. Now what we do, at each SOC, at 10% SOC, we calculate the values of R, R1, C1, R2, and CP, and then plot it in the graph below. Similarly, for 10 other positions of SOC at 10%, 20%, 30%, 40%, and we plot the corresponding values of R, not R1, C1, R2, and C2, and R2 and CP. Now, what we have introduced here, a novel kind of attempt, is that we have plotted it against SOC. So what we want to see is the variation of these parameters as a function of SOC, so that we can understand how we can try to estimate SOC in a correct way, in a more accurate way, to see how these parameters actually depend on the SOC. So we tried the repeatability test with 3 cells with different aging. So as you can see, all the 3 conditions and all the parameters, you can see there is a similar trend. As you can see, the shape is similar in C1 and R2. In fact, it overlaps completely, giving very nice trends. So it does prove that this repeatability test does prove that the parameters actually depend on SOC. And this is a fractional order model that we have designed. So as X1, where X1 is a state of charge, X2 is a voltage across R1, C1, and X3 is a voltage across R2 and CPE. So these are the definitions of fractional derivative. So we are using Caputo derivative to solve the previous equation. And once we solve the equation, we get the values of X1, X2, and X3. Now what we do, we introduce physics-informed machine learning. So what we do in this kind of machine learning, we give the experimental data, as well as we give the data, the outputs of the fractional order circuit model. Both of them we give as an input to the neurons, to the layers of the learning algorithm. So that is how we introduce physics-informed machine learning. So it will take information, both the physics model as well as the experimental data, and try to minimize the error in the loss function. So this is the fractional order, the output we got. So the start is the input current. So that is a UDDS profile. That is the real-time profile, actually, the input current, that how a driver, it depends on how a driver is driving, like this increase of the speed and the decrease of the speed. Correspondingly, it is reflected into current, increasing like charging current and discharging current. So discharging current is positive, charging current is negative. And then we plot the output terminal voltage. As you can see, the experimental is blue in color, and the red part is in red in color. So after 200 seconds, we see a slight divergence. So that is what we are trying to minimize in the learning algorithm. So it is already closer to the experimental data. And now what we're trying is to minimize the error. So that is how a less amount of data is required for the learning algorithm. So the research gaps, as you can see, the IOMs means integer order models. They use complex nonlinear partial implications, which are computationally cumbersome. So electrical circuit model is given instead of the partial, we are replacing partial differential equations with an electrical equivalent circuit. So it's simpler to solve. And integer order models are not able to capture physics of the battery. So that is why that flat part is not flat part of the curve, the SOC curve that I showed initially couldn't be reflected by integer order models. So that is why we are taking a physics informed machine learning algorithm and a fractional order model that has more flexibility to capture the underlying dynamics. And lastly, as I said, the model-based methods are white box models, data-driven are black box models. So we are introducing a combination of both, and that is, I can say it's the zebra model. So these are the SOC estimation and curves. We are still working discharge and discharge curves of the LFP batteries. So the future prospects of LFP. In 2025, the LFP global production of capacity will be around 770 gigawatt hour. Ford announces commitment of $29 billion to electric and self-driving cars. And 2030, Volvo to go all electric. 2035, GM will go all electric. 2023, Honda will, it has formed partnership to recycle old EV batteries. So that is second life applications. And Porsche and Custom Cells invest in joining to produce specialty batteries for racing. So racing cars, they will require more batteries. So as you can see, in the initial part of the presentation, I started how there's a shift towards LFP batteries. And now you can see in the next 5 to 10 years, there's a huge production and prospect of LFP, provided we are able to correctly estimate the state of charge. So this is the proposal in a nutshell. Objective 1, Objective 2, Objective 1 is the fractional order part. Objective 2 is the machine learning part. Objective 3 is testing and validation. So this is the flying car of Harry Potter. So this is what at least I grew up reading and watching. And so I always loved this flying car with the Harry Potter and his best friend Ronald in that. And that who knew that when after 15 years it became a reality. So this is the first flying car that was introduced in 2022. It is powered by Tesla. This flying car can also operate as a drone, meaning it can operate as an unmanned aerial vehicle in terms of earthquakes and floods and rescuing operations. It is ultra light. It weighs only 86 kilos, which is around 100 pounds. So according to US driving rules, if it is only 100 pounds, you don't need a driving license. So any one of us can fly this, since it weighs only 86 kilos. And it flies at a speed of 63 miles per hour, that is 100 kilometers per hour. Units sold. Now, who would buy this? When it was introduced in 2022, this Jetson, it's called Jetson 1, in collaboration with Tesla, it produced only 25 units. They thought they will sell 25 units in the entire year. But 25 units got sold out in 1 week. And in the whole year, they sold out 400 units. And they plan to go over 1,000 in 2023, and who knows, even more. So this is the next generation transportation. For instance, if like today, I came to this talk using a taxi, who knows, next time I would be flying from Longmont to Denver using a flying car, and then you skip the traffic on road. So this is powered by Tesla, and this is powered by a battery. So this is also where the future of battery lies, LFP, NMC, whatever you call it. So, okay, this is our energy controls group at UC Berkeley. So this is what happens at happy hour, go drinking. We go meet once a week on the Friday evening, and that is where, even if there are people who do not come to lab regularly, but they always attend this happy hour. So so even if somebody is missing out on research, they don't miss out on the happy hour, and we all meet together to discuss on our research. this is also an exchange of research ideas. Excuse me. So Professor Borah is in the top row, third from last, the one in the black hoodie, and the speaker, yours truly, is fifth from last, or third from left, I mean upper row. And the next is fractional modeling and control applications. I don't know if the audience is interested in this, or should I go ahead or not with this?
How much time do you have? Because I remember you said you need to leave.
I have time now. I have to reach at.
I'm interested. I mean,
Okay, so I'll give a quick. I'll try to complete within 4 to 5 minutes.
yeah, definitely. No problem.
So this is chaos, and chaos is extremely sensitive to initial conditions. It's a mathematical phenomenon, and it is aperiodic in nature. So where do we use chaos? Well, for example, let's start with biological systems. There are so many diseases. Migraine, we worked with migraine. We worked with Alzheimer's disease, Parkinson's, HIV, Ebola virus, dengue, and also COVID. In all of the systems, we found chaos, but we do need chaos because it is extremely sensitive to initial condition. It may give rise to unnatural, such extreme sensitivity could give rise to unnatural phenomenon in the body. So we want to, so this is a fractional order model of Parkinson's disease, where I have applied fractional order modeling as well as control. So we want to control chaos. And after we control chaos, so this is the chaotic attractors present in a Parkinson's model. So this is in sickle cell anemia. This is an Ebola virus. So this is in plague models, cancer, HIV, COVID. So this is where we all try to control chaos, and it has been successful. It has been found that fractional order control methods gave more efficient control than integral order methods. So the part of it was also, we collaborated with Georgia Institute of Technology, like Professor Fenton and Professor Cherry, and we published it in terms of diseases like HIV, dengue, migraine, Parkinson's, and Ebola. And also there is Professor Cheng from University of California, Merced, and we published on COVID on that. And this work was also awarded the Young Scientist Award by the government of, how to go back? Okay, the government of India as a Young Scientist Award. So that I skipped that slide. Again, fractional order model can also be used in variable speed drives. This is a permanent magnet synchronous generator, PMSG, that is electrical machines. And here also, so these are the various parameters that are defined by the state equations. So here also we use fractional order control, the circuit, to stabilize the chaotic behavior. And this is another fractional order chaotic system. So we are using it. So these are like different attractors. These are multi-scroll attractors. These are coexisting attractors. These are multi-stable attractors. These are the circuit implementations we have done in our lab. And it is applied to secure communication. So if I am the sender, I'm sending a signal, that is one in red, and there's a receiver, this one is yellow. So while the signal is being transmitted, we mask it with a chaotic signal, and the masking signal can be seen in the green. So while the sender is receiving the sending the signal to the intended receiver, so a third person or a hacker cannot easily hack or break this signal because it is a chaotic signal. It is highly sensitive to initial conditions. A slight change in the parameter 0.00001 would result in a complete different dynamics. So it's very much useful in encryption techniques. So the previous was the nursery rhyme Mary had a little lamb, and now this is an audio signal. This was my voice that I recorded, a short 8-second recording of my voice, and then I masked it, and then I sent it to a receiver, and the receiver could retrieve the signal.
The receiver knows the
Yes.
to the
Yes, but-
parameters of the.
So they have to know only one set of parameters, and the control algorithm is designed. Even if you know half of the parameters, it could be retrieved. So this is the original image, sender, and the encrypted image in between, that is a masked image while sending. So if I want to send any confidential message, confidential pictures, videos, audios, and the right side is a decrypted message at the receiver's end. So these are different. Okay, then fractional order modeling. We also work in magnetic levitation systems. So we design controllers for magnetic levitation systems. Now we intend to extend it to a BRICS proposal. So BRICS is Brazil, Russia, India, China, and South Africa. So we have combined a proposal and submitted it. It has crossed to screenings and is at the final stage. So here we are working on long distance and short distance magnetic trains. A sample of it was already made in Brazil lab, our Brazil collaborator. So they have made a magnetic train that runs from his lab to another lab in the building, and he can carry 10 of his students in the magnetic train. So we are trying to extend it to the next TRL level.
So BRICS organization funds these.
Yes,
they
it
accept
funds.
proposals. And
Yes. So that is it. So that is it. Thank you, everyone. And I'm here to take questions and maybe suggestions. Thank you.
Okay, so we will open it up for our audience. Anyone would like to ask questions to the speaker?
Can we hear anything that they say out there?
Yes.
Any questions?
One from data.
What is
Okay.
here?
LFP is still based on intercalum.
What is interconnection? I'm not sure.
I don't know. So Jada, would you like to, I mean, the speaker is asking what intercalation is. Would you like to speak perhaps?
What does interconnection mean?
Yes,
Can you hear me?
yeah, that we can. Go ahead.
Okay, so yeah, the intercalation is the how the lithium-ion battery works. The secondary battery, lithium secondary battery is different than the primary lithium batteries. So that's what those people were awarded Nobel Prize last in 2019. So I was curious, this LFP is based on the intercalation, just like lithium-ion batteries.
I'm not sure which part you're referring to. We are presently working on secondary, as you mentioned, we are working on secondary lithium-ion batteries and LFP batteries. We are not working on the electrical chemistry part, and the people who won the prize, they were working on the electrochemical part of the batteries. We are mostly working on the electrical part of the batteries and the circuit elements. So that is all I can tell you right now, but I can go through it and let you know in your mail.
Okay, so I have another question about the your presentation. I couldn't catch the physics-informed part of the machine learning. Could you elaborate that a little bit more for me?
Yes. Do you want me to go to the slides or? So in physics informed machine learning, so in the machine learning part, while we are giving this part, the big data, in machine learning, we use a large amount of data as an input to the input layer. It goes to the hidden layer, calculates the weights, and then we get the output. So it's like kind of, we need a large amount of data for training, testing, and then validation. So in physics informed machine learning part, what we are doing is that we are giving some amount of data, not all the huge amount of experimental data, and the rest part of it is compensated by the physical laws we get from the electrical equivalent circuit. That is, while we solve the fractional order model of the circuit, we get the physical state equations of x1, x2, and x3, say that which may represent voltage, current, or the SOC, and then we feed it into the machine learning algorithm as an input. So that is how the physics part of the model is given as an input to the machine learning algorithm. And in that way, it is not as computationally intensive. It is faster than regular ML algorithms. And it tends to give more accurate result because it also has the physical laws part. Was I able to answer your questions, sir?
So what kind of physical laws are you talking about?
Yes, in our case, we are mostly considering the electrical equations, the fractional order equations that we solve. Those are mostly voltage and current equations, the relationships between voltage, current, and SOC.
So at that part, that I wasn't quite sure. So it looks like you're trying to learn the output of EIS using neural network. Is it right?
No, the output of EIS is used to model the fractional order model. Oh yes, I mean you were talking about the voltage, terminal voltage.
Yeah.
Yes. Sorry.
So what you're trying to do is you're trying to figure out the parameters in that equivalent circuit from the data.
We are not trying to find out the parameters of the circuit because we have already done that using the fitting curves, as you can see here.
Yeah.
So you're trying to train that CPE block, right?
Yes, we are trying to train that and
And then nevertheless, the other parameters, they may also change
they will
with
change
the
with state of charge as their function.
so you have a functional model for them.
Yes, we have a functional model. So the output of this would be like x1, x2, and x3.
Where is X?
Just a minute, I'm showing you. Just a minute. Yes. So as you can see, this is the fractional order model. So these are the equations, like the electrical equations I talked about. So these are the equations, and the solution of this, we are calculating the solution of this using Caputo derivative, the definition of which I showed. So this will give us x1, x2, and x3. So x1 is the state of charge, x2 is a voltage across R1, C1, x3 is a voltage across R2 and CCP. And once we get the output of this, we feed it to the machine learning algorithm along with some amount of the experimental data. So that is what physics inform. Am I clear, sir?
Moment.
I was expecting these not to be integer equations in some of your later results too.
In some of this?
Well, so like when you take the fractional derivatives, I was expecting to see the exponents not be integers.
Exponents, okay. So here, while I have calculated using alpha 1 and alpha 2, I have kept integer order. Alpha 3, I have taken, I have taken 0.55.
Okay, but even like some of your later equations, right there,
I can show you. Okay, so as you can see here, this is while we are fitting the curve, you can see the value of alpha. It ranges between 0.54 to 0.58. So I took it between 0.55 for alpha, and that is alpha 3. I mean the last equation. And alpha 1 and alpha 2, I've kept it integer order because there we haven't introduced any fractional order element. So that is a general way I have represented alpha 1, alpha 2, and alpha 3.
So I also had a question regarding that very same slide. So you said that you have functions for R1, R2, C1, and whatnot that might depend on the state of charge, right?
Yes,
so those functions are characterized by some parameters, right?
Yes.
Yeah, and those parameters, they might change during operation, right?
Yes, we are fitting the function depending on the curve that we got from the experimental data.
Yeah, my question at the end is that, because a battery is always going to be utilized in some sort of a closed loop setting, right? Where you will have real-time data, measurements, this and that, right? And then why not using that information to, further adjust your model, not just the parameters of the functions perhaps, but also, whatever neural network you're training in there, that neural network can be adaptive, say, perhaps using Q-learning, those kind of things, where you can do real-time learning and
the experiments in here that we carried out, they are open loop experiments.
right.
And the kind of learning algorithm that we are going to do, that will be a kind of closed loop algorithm.
Mhm.
So we are trying to incorporate both parts, as I
Mhm.
said. So if we make it real time, we are still trying to make it real time. At present, this is only offline type I showed, like solving the equations and then sending it. So once when we make it real time, we have to take into consideration the closed loop part, as you have said.
Exactly, yeah, yeah. And my point is that, like when you have real-time operation, there'll be information that you can use to further refine the model that you are presenting.
Yes, and also that real time requires also there are a lot more other factors as well. For example, the battery, the aging of the battery after like 500 cycles or 1000 cycles, or so 20% aging, 50% aging. So that kind of factors also have to be taken into account. So
Mhm, mhm. Very good. So any other questions from the audience?
I want to help to answer the first question.
Can you speak louder, Yuchen, please?
Oh, sorry. Could you hear me?
Yes.
Okay. I want to help to ask the first question answered by asked by Professor Park about the LFP and the MC. LFP and MC basically they are all like lithium-ion battery or lithium like secondary battery. But LFP and MC, the difference is basically they are the different cathode material used by lithium-ion battery. LFP stands for lithium ferrous phosphate, or people usually say lithium iron phosphate battery. And the MC is a nickel magnesium cobalt. It's another material used in a lithium ion battery. So usually LFP battery has higher discharge rate and more stable. So that's why in last seminar I was asking if LFP battery has to have a battery management system. And NFC usually they have a higher energy density, but they are more prone to high rate discharging stuff. This kind of issue. Yeah.
thank you for the suggestion.
Any other questions or comments from the audience before we wrap up here? Seems that there are no more questions. So at this point, then I will just thanks the speaker again. And yeah, thank you everyone for attending this very last minute talk. And yeah, we will connect again for people that are taking the seminar class. We will connect again this upcoming Tuesday. And I will, we will send the information for that. Okay.
Thank you so much. And I would also appreciate suggestions. So please, my mail ID, I think Professor Nand would share my mail ID maybe if you have any suggestions and any intention of collaboration. I'm very interested in collaborating, and I also have heard about the battery equipment we have in our department. So let us use it and utilize our resources and make a collaborative research.
Well, thank you so much. Yeah. Thank you guys. Have a good day. Bye-bye.